Hi, it's Professor Angela Rasmussen again. We're going to go through an example with an inductor to find IL and VL. So again, today the password is examples, so make sure that it's all small cases or small letters, and make sure to take that annotated daily quiz for today's lecture. So to find an expression for either the current or the inductor or the voltage, you need to remember you need to draw 4 different circuits. So the time before a change happens, the time at the change, and the final time. And then for the final time, you also need to find RTH at the final time for tau. So we're going to look at this and decide, well, what is the state of the circuit before the change happens? So looking at the switch is going to determine that in this case. So the switch shows that this closes at time 0, which means before it happens, it's open. So that's going to be sitting there for a long time, and we're going to use that to find the first information. So I call it 0 minus. You're going to determine what the switch is doing and then also what the inductor is going to be modeled. When it's sat there for a long time, that means that the inductor has no more current and the voltage across it will be 0. So di dt will be 0, which means voltage is 0. And then the switch, we said, is closed at time 0, so that's the change that happens. So right before it, it will be open. So as we look at this, we are going to find what doesn't change between the time before a change and at the same time for inductor is that the current is what we want to find. So we want to find this IL. Well, as we see here, if we put ground, then there's no current in this one because it is open. And then if we don't see it, then we can do node voltage here. So it would be Vx over 60 plus Vx over 15 equals 0. And the only way that's true is that this goes divided over, and 0 times this number is still going to be 0, so Vx will be 0. If Vx is 0, then IL also has to be 0. So IL would be Vx over 15. And so IL is 0. And so at the next instance, which is at the change itself, this is going to be what we consider the initial time, is right at the change time. So at this time, we want both so this didn't specify, but VL is going to be the voltage VL across that inductor, and IL is the current going through that inductor, and we're going to keep them the same polarity. And so VL will stay the same here. And what we model this at the initial time is in the transient state, which means we need to model this as a current source. And the value of that current source is going to stay the same as the value we just found, which was 0. So that means no current is flowing, and this branch actually looks like an open. The voltage across it, because there's no current on that right side and I'm grounding it, this is going to be 0 volts on one side, and then I note that this is going to then be the node VL that I want to solve for. And so the voltage across this VL, the switch will be closed at the change. So now VL minus 15 over 20, VL over 60, and then the right side branch is again 0. So combining these as a common denominator, I get 3 plus 1. Over 4, and this ends up being 11.25. So this will be my initial value for voltage, and then my initial current value will be 0. So I'm going to use both of those as their initial values. So at the final time, again, it sat there for a long time. And so the inductor again is a wire, switch is closed. And then I need to find the voltage VL is easier in this case because that's just a wire, so VL will be 0 for this case, and then I need to find the current in this branch, and so I'm going to just call this Vx this time, Vx minus 15 over 20. So I can find a common denominator, or I can just find a number, the number of all of these. And 15 over 20, and then this is going to be 1 over all of those. 1 over 20, 1 over 60, 1 over 15. And this ends up being 0.5625 volts. So if that's Vx, and then IL will be Vx over 15, which ends up being 0.375 amps. So this is then my final value for my current, and my final value for voltage is 0. And then I need to find tau. So for tau, again, the final state, which means it's closed for the switch. And then for tau, we're going to take A and B as the terminals of the component, and then we're going to take out the component. So now we also have to remove the sources. So a voltage source will become a wire, and a current source becomes an open. So here I have a split, so this is going to be RTH is going to be 20 in parallel with 60, and then plus 15 to get to the other side, and this ends up being 1 over 20, 1 over 60 plus 15, and then RTH here is 30 ohms. So tau, remember this is an inductor, so it's L over RTH, and L was 3 millihenries, and so this ends up being 0.1 milliseconds. So for both expressions, our final value for the current is 0.375. Our initial one was 0. .375, and then e to the minus t over the 0.1 milliseconds. So this will be in amps. So this is our expression for the current. And then for voltage, our final value was 0. And then 11.25 volts, and then 0, e to the minus t over 0.1 milliseconds. And these are in volts. So also note that these are all only valid for both of these for time greater than equal to 0. So these are only valid after that switch has happened. So another option of doing this is to get IL of t, and then you can find VL of t from L DIL of t dt, and you can just differentiate that. So if we differentiate that, you're going to have 0.375, so minus 0.375, and then, oh, you need L in front, sorry. So L was 3 milli. And then remember the exponential, it's going to be minus 1 over 0.1 milli. So the minuses become pluses here. And then e to minus t over 0.1 milliseconds. So multiplying this out, we end up again with 11.25. E to the minus t over 0.1 milliseconds, which is the same. So you can find it either way, either finding one equation and then using the memorized equation, or you can find the initial and final values and put it into this form. All right, thank you for watching this example.